Hi, welcome to Processing Motion Part 5. Um, Today's topic is orbits, orbital motion, which involves a lot of math with ellipses and looking up some data about the solar system. So, if you ever want to send one of your robot friends to Pluto to take photos like this, you have to understand orbits, right? So let's get on with the math. Then we'll create our model of the inner solar system, which is Mercury, Venus, Earth, and Mars. And we'll draw it. We'll draw the orbits. We'll draw the paths that they take, and make sure everything is scaled correctly. Okay, so let's switch over to the math. Most orbits do not follow a perfectly circular path. The majority of them are at least slightly elliptical, and some of them are highly elliptical. So an ellipse is basically just kind of a circle that's been squished a little bit. So let's define some mathematical quantities. The major axis is the one that goes across the long side of the ellipse, and the semi-major axis is designated by an A, which is halfway across. The minor axis is the short side of the ellipse, and the semi-minor axis is designated with a B. Right, so long side, half of the long side is A, half of the short side is B. And if you look this up in a textbook or something like that, you'll see the equation of an ellipse is x squared over a squared plus b squared. Sorry, a little distracted. There's some sirens and whatnot outside. Y squared over b squared equals 1. Right, so x and y are your traditional coordinates, x corresponding to the horizontal distance from the origin, y corresponding to the vertical distance from the origin. A and b are defined in the diagram below, and hopefully we know what 1 means, right? So when we create our program, this equation is very tricky to use. So instead we're going to use the parametric form. We're going to use some parametric equations, and I need to go over those, I think, in some detail and prove that they're equivalent, because most of the time we don't really use these. So we have x equals a cosine of t, and we have y equals b sine of t. Now this parametric variable here, t, it's a little bit tricky to understand. It's not really an angle. It can be time. In fact, it works really well as a time variable. Or it can be really any physical quantity that you want to represent. So when you see these parametric equations, just keep in mind that t variable works really good as like a rate or a time, but you need to define it and kind of know what you're doing with it. For us, we're going to use it to represent orbital speed, to control how fast our planets are going around their orbit. But before we get there, let's prove that this system of equations here is actually equivalent to the equation of an ellipse. Okay, so we're going to do a little bit of a rearranging. In the first equation, we'll divide both sides by a, so we just get cosine of t on the right side. On the second equation, we'll divide both sides by b. So y divided by b equals sine of t. Okay? Then we want to square both equations. So x over a squared equals cosine squared of t. And y over b squared equals sine squared of t. Cool. Now we're going to add the equations together. We're allowed to do that because we can right? Any two valid equations, you can add them together, and the result is a valid equation. So we get x over a squared plus y over b squared equals cosine squared of t plus sine squared of t. Now, if you've taken a trigonometry class, or you've studied trigonometry, you probably recognize this right side of the equation. Cosine squared of t plus sine squared of t is one of the famous trigonometric identities, and it's that quantity is always equal to 1. So cosine squared of t plus sine squared of t equals 1. And so I can substitute in 1 on this right side of the equation, and I get x over a squared plus y over b squared equals 1, which is the equation of an ellipse. So we've shown that these parametric equations are completely equivalent to the standard form of the ellipse. Let's look at this in a little bit more detail and kind of relate it to the orbit of planets. Okay, so as a reminder, this semi-major axis is designated with an A, and the semi-minor axis is designated with a B, right? There's a couple other geometrical points that are important, and those are the foci. So there's a focus here, and there's a focus, another one, equidistant from the midpoint. Midpoint of the semi-major axis and the semi-minor axis is at the same point. I'm going to call it M. And the distance between one of the foci and the midpoint is designated with the letter C. Okay? I think this is the last new letter I'm going to introduce, so bear with me. The definition of eccentricity of an ellipse is given by C over A. So if you take the focus point and move it further away from the midpoint, you get an ellipse that's more eccentric, meaning the circle is more squished. And if you move the focus to the midpoint, then you have basically a circle, right? So this is our definition of eccentricity, and we're going to need to use that when we get some of our orbital data. Couple more things. This A is equivalent to, the semi-major axis is equivalent to the mean distance from the sun when we're talking about a planet going around our sun. So imagine you have a planet and it's following this elliptical path. The elliptical path is actually centered at the midpoint. However, the sun is not necessarily at the midpoint of that ellipse. And the higher the eccentricity, the further away the sun is from that midpoint. So let's erase this foci, or this focus point here, and draw the sun at that location. So one of the foci, that's where the sun is. So notice that the planet is going around and it's orbiting the sun, but its orbit is centered at the midpoint, not at the sun itself. The more elliptical the orbit, the higher the eccentricity, the further away the sun is from that midpoint. So if you got a really exaggerated ellipse, like, I'm not very good at drawing these things, and you had a planet that was going around, the sun might be like way over here, where the planet or object gets super close to the sun on one side of the orbit and then gets quite a bit further away from the sun on the other side of the orbit. Okay, so to get A from data online or wherever, what textbook you have, you just need to know the mean distance from the sun. And for b, we can define that mathematically, which is a times the square root of 1 minus e squared. And remember, e is the eccentricity. I can just plug that in here. Okay, so we know A, we know B, we know the foci. We've defined eccentricity in terms of this C value, and we understand that, excuse me, a planet goes around in orbit following the path of an ellipse. So taking all of this, we can look up some data about the inner planets, and we should be able to draw a processing sketch that follows these rules in order to create a model of the inner solar system. So let's switch over to the computer, and first we'll go over a spreadsheet that I use to keep track of all the data, and then we'll plug those numbers into a processing sketch. All right, so our reference shout out for this video goes to Hyperphysics. As you can see, there's tons of topics. There's a ridiculous amount of information on this website. Lots of data, lots of stuff. So for us, we're doing orbits, which goes in astrophysics. We're talking about the solar system, and we want some data. There we go. So planetary data. We get our mean distance from the sun, which we're going to use as that A value, which is the semi-major axis. We get inclination here. Our model is going to be two-dimensional, so it's not going to account for inclination, but if you wanted to create a three-dimensional model, you would need to look up the angle, and actually you would want this one. This is relative to the Earth's orbit. So for example, Mercury is tilted, its orbit's tilted 7 degrees relative to Earth. So that's pretty substantial compared to Venus, which is 3, Mars, which is a bit less than 2, and so on. Pluto's all the way is tilted 17 degrees, right? So it's a little bit different. Eccentricity, we're going to need to know that for our model, right? So I'm going to take all of these numbers, and I think that's it. So let's go to the spreadsheet where I summarized all this data. Okay, so semi-major axis, I was able to take that directly from the mean orbital distance. The semi-minor axis, I calculated using semi-major axis times the square root of 1 minus f3, which corresponds to the eccentricity, squared. Eccentricity I got directly from the data, but I used it to calculate these values. Then I scaled them to pixels so that the numbers made sense for a processing sketch. And I decided after looking at it that multiplying the orbital distance in million kilometers by 1.5 kind of scaled it up a little bit into pixels and gave me numbers that kind of made sense. These are semi-major axis, so they're half of the full axis. And with processing, when you draw an ellipse, you enter the value of the full major axis and minor axis. It should say minor. So these I just doubled. D3 times 2, so I just took that square times 2, dragged it down. All these are simply double what these are. As I mentioned, I got the eccentricities from Hyperphysics. Now, this is a little bit tricky here. I rearranged the eccentricity equation, which is C divided by A. And so what I did is I did the eccentricity, which is this value, times the A value, which is the semi-major axis, to get a shift, right? So as I mentioned before, the planets aren't centered around the sun. They're centered, they're going around the center of the ellipse, and the sun is not necessarily at the center of the ellipse. So what this eccentricity value allows us to do is to see how much the sun is going to be shifted over. So by multiplying this value by this, we're still in pixels. So at this scale, the orbit of Mercury needs to be shifted over by 18 pixels really. Venus and Earth have very low eccentricity, so very small shift. The sun is actually very, very close to that midpoint of the major axis and not very elliptical in orbit. And then Mars does have a bit of eccentricity, and it also has a larger orbit, so the shift gets proportionally a little bit bigger. Okay, so we'll be able to draw the ellipses no problem, but when we draw planets orbiting, they need to go around at a certain rate. So these are the orbital periods of the inner planets: Mercury, Venus, Earth, and Mars. Earth's orbital period obviously is 1 year. And what I did here is 2 pi divided by the orbital period to get the angular speed. And these are the numbers I'm going to use to control how fast the planets go around, how fast they go around in their orbit. These I'm going to create, these are the diameters of the actual planets in kilometers. So notice over here, the orbits are measured in millions of kilometers. And these are really in kilometers, but these are thousands of kilometers. So the scale is going to have to be different, right? To fit on a processing sketch, I can't scale them at the same rate. So what I did is did 3/1000ths of a kilometer. So I just took this kilometer times 3/1000ths to scale it down to something that would make sense in terms of pixels. Circles on the screen that are going, like 38 pixels in a processing sketch is pretty reasonable size. So that's how I did the scale. And at this scale, since the sun has a diameter of about 1 million kilometers, its diameter would actually be 3,000 pixels at that scale. So let's put these numbers into a processing sketch. For the setup, we'll just create the size. I'm going to do 850 by 750. And that's it. And then we'll go to draw. So we want to do 2 things. We want to draw the shape of the orbit so we can see it. And we want to draw planets following that path, right? So we'll start by drawing the shapes of the orbits. And we'll create a black background, since black traditionally is used to represent the color of space. I'm going to use a translate function to basically put everything centered, put the origin at the center of the window. And for our orbits, or for our orbital paths, we don't want them to be filled. We want them to be just lines. And I'll draw them white. So we're going to have 4 ellipses representing the orbits of Mercury through Mars. Okay, so what goes in here? First, we need to know how much they shift by, which are these values here. So Mercury is going to be shifted by about 18 pixels. And Venus will be shifted by 1. Earth will be shifted by 4. And Mars will be shifted by 32. And they will not have a vertical shift. So this will just be centered. Next we need the major axis and minor axis in pixels. So for Mercury, we have 174. I'm going to round to whole numbers here. And 170. For Venus, we have 324. and 324, so almost a circular orbit. Circular enough actually to where we can make it a perfect circle for our model. Same with Earth. And for Mars, it's going to be 684 pixels by 681 pixels. Okay, so oh yeah, missing a parentheses here. Okay, so let's play it and see if it shows up. Cool, so there are the orbits. You can see the center is here from a Mercury standpoint, but you can see it's kind of shifted, right? So the true center of our screen is about here, and these orbits are shifted a little bit because of that eccentricity. Okay, now for the hard part. We want to set up our parametric equations basically into an ellipse function that draws circles. So we draw circles representing the planets, and then we build in the parametric equations in the position of those ellipses. So for Mercury, we want to be like a grayish color. And what we want to do is use these values here to control the parametric equations. So what we will do is 87 times cosine of t, but we're going to do t me for Mercury. And then we want to do 85 times sine of TME. Those are the parametric equations showing us the location. And then we have the pixeled size of these planets. So right here. So for Mercury, that's going to be 14. 14. Okay. Now remember that the orbits are shifted a bit. So for Mercury, the shift is 18. So we need to add 18 to this. Okay. And then we need to initialize our TME variable. See, we haven't created that yet. So these are going to be decimals, so call it a floating variable. And we'll initialize it at 0. And while we're up here, let's go ahead and create for Venus, for Earth, and for Mars. So these are the parametric variables. They're going to control how fast our planets are going in orbit. Okay, so basically we're going to create 3 copies of this. So this is Mercury. And for Venus, we want sort of an orange color. Tried these out earlier, and these numbers end up looking pretty good. And then back to our spreadsheet. Remember, we're using these values here to determine the path of the planets. Okay. Sorry, these. So this is going to be 162, This is going to be also 162. And our shift is going to be a little bit different for this one. It's only for Venus, it's only going to be a shift of 1, right, which is that box there. And then our pixels, Venus is going to be 36 by 36. Okay, cool. Spread these out just a little bit so they're easier to see. This one we're going to make Earth. And we want kind of a bluish color, right? So that one works out pretty well as 245, 134, and 106. Actually, I take that back. That'll be the next one. That'll be Mars. I kind of noticed that was a little bit too much red. Okay, there's our fill. For Earth, we're going to be at 450 and 450. Take that back. 225 and 225. It's easy to get these two mixed up between semi-major and major, but when we're doing the big ellipse that the path follows, we want major, and when we're doing the parametric equation, we want semi-major, right? So this shift is going to be a little bit different. This is going to be 4. We're going to shift by 4 pixels, just like we did here. And let's remember this is Venus, so we need TV here. And this is Earth, so we need TE and TE. Okay, one more. Okay, so Mars is the one that needs a lot of red. So this is the one that gets that 245, 134, 106. This is going to be Mars. 342 with a shift of 32. And this is going to be 341. Scrolling over, we get our pixels for Mars as 20. It's a bit smaller than the previous two. Okay, I don't think we've done anything terribly wrong yet. TMA to distinguish between Mars and Mercury. All right, let's see what it looks like. Let's see if it actually follows the right paths. Oh, we have not told our t variables to change, to do anything, which is important. So we want TME, which is Mercury. We want those to be based on the angular speed, which are these values. Now, if you plug these into the parametric equations, as is, this 26 value, 10.6, that's super fast. So what I did is I moved the decimal to the left several times and got 0.026 instead. and we want Venus, oops, kind of mixed and matched my notation here. So we want TME plus equals 0.026, which means each iteration we want to add that amount to our value. And for Venus, we want to use 0.01. For Earth, we want to use 0.00628. And for Mars, we want to add 0.00334. There we go. Now these t variables will change as the program goes, and so that these will be updated and so on. And I'm going to add no stroke to our planets. That tends to look a little bit better. All right, let's try it again. Now they're moving. Excellent. So you can see these elliptical orbits are shifted a little bit, and planets seem to be going around nicely. We have Mercury, Venus, Earth, and Mars. And for one last point, let's go ahead and put in a sun. We will not be able to draw it to scale of the planets because it would take up the entire screen. I actually calculated that value. Like I said, it would be 3,000 pixels, and our screen is less than 1,000 pixels here. So the sun at this scale would not the same scale of the planets would not fit, right? So what we'll do is make it kind of yellowish, and we'll put it at the origin with a pixel size of 3. Pixel size of 3 scales it to the actual orbits, so that puts it on this scale over here. So that little dot there is the position of the sun relative to the orbits, and it's actually the correct size compared to these orbits. Whereas these the inner planets that are going around are scaled to appear much larger than they really are. The sun at this scale is actually to scale with respect to the orbits. And we can see that Mercury gets significantly closer to the sun on this side than it does on this side. It gets further away over here. But we can see that Earth and Venus are pretty circular, and so they stay about almost equidistant from the sun throughout their path. The orbit of Mars is a bit more elliptical. So our P5 transition will be very easy with this one. There's no vectors. So really we just need to get rid of this floating variable notation and change this to var, which is short for variable. We need to change our void to function. Size goes to create canvas. All this stuff should work. We play it, and there's our solar system again. Right, so using the elliptical model, we've been able to create a 2D model of the solar system. If you want to create a 3D model, you need to understand the inclination of the orbits as well, because they're sort of tilted compared to each other. But this is a really nice top-down view, and it worked out pretty well. Okay, thanks for listening. That's the end of the video, and I'll see you next time.